The background math that we're going to start with is right out of the first chapter of the Barron's Review book. So remember I said to get that book to have throughout the year? If you could get it soon, I would recommend it. And the reason being, I'd like you to be prepared all year as we're going through. I don't want it to be like, oh, we come, February, and now you get a review book, and now you got to start reading the entire review book throughout the year. I want you to have a book that takes you along the AP curriculum. So the book that we use, Halliday, is a great book. It's next door. But it's a heavy physics, calculus-based textbook for college. So we're only going to be covering, say, the first 6 chapters or whatever portion of that book. And it's not a book that's like a line for the AP exam where every chapter goes along with what's on the exam. You'll notice I'm going to be like picking and choosing topics that we cover in there that are in the text that are also on the AP exam. But the Barron's book specifically just runs you through topic by topic of everything on the exam. So if you can do that over the weekend or something, get a copy of that book so you guys have it. Just, you can take notes in it. You could read it regularly as we go through it. So when we're starting to cover one-dimensional kinematics, that's chapter 2 in this book. When we start to cover projectile motion, that's chapter 3. So it would be like a really good suggestion for you to be reading regularly as we cover these topics out of the review textbook. The review book gives you the real specific stuff you're going to need. It doesn't really go into as much depth as we're going to, but it's a nice overview as we're doing all of our work for you to see the real gist of it, or why we're covering each of these topics, or what are the specific things you really need to know from each of those topics. With that said, let's start this. I usually walk around a lot. If you notice, I have this on here. My wrist has been really bad. I heard it this summer. And holding the iPad the other day with you guys and with the honors class, I couldn't even clench my wrist at the end of the day. So unfortunately, I'm going to have to write up here for a couple days. So I'll try to move as I talk, or maybe move my iPad here. I don't like to stay here, but I'm going to do that just for a little bit. So the first thing we need to know are the phrases vectors and scalars. Vectors and scalars. You're probably familiar with vectors from last year because of the fact that you use that phrase all the time, whereas scalar might not be as familiar because I don't even think I use the word scalar in my course. I use vectors though. A scalar is just not a vector. We'll discuss how they're different. Can somebody tell me what a vector is by definition? What a vector would be? It contains 2 things. I can give you that hint. 2 things that are important for a vector. Chip?
It's like quantity and then also it has direction.
Very good. Quantity and direction. You could say magnitude is the usual word. Quantity works. So it's a magnitude. This is vectors. It's a magnitude and a direction. What are some examples of vectors? What are some examples? Velocity. What else? There's a lot. Any example of vectors? Acceleration. Outside of motion. What else? Outside of motion. What was something throughout the year you learned that maybe had an angle to it and mattered because there was an angle involved? When was there an angle involved? We broke things into components and not initial velocity at an angle or something like that. Spence? Torque works. I wasn't thinking torque, but torque works.
Work.
Say again?
Work.
Work matters for direction. One that's more basic than both of those that is involved. Force. Force is in torque and force is in work. Force times distance, right? Torque, force times lever arm. So force is really the vector quantity that makes work and torque a vector quantity. So force is our third that we should really recognize here. Now again, a lot of these quantities make other things vectors as well, like Spencer said with torque and like Max said with work. So if you take a vector in a formula and multiply it by something else, it's still a vector. So if the vector length were something like this, let's say the vector were a 1 Newton force at an angle of 25 degrees. And let's say that's my vector. And I doubled my strength, doubled it. What happens to the vector if I double the strength? Yeah, it just turns to 2 newtons. What doesn't change though? The angle. So when you magnify the amplitude of a vector, meaning multiplied by something else, it changes the magnitude itself, or as Chip said, the quantity of that amount. but it doesn't change the direction. Okay, and that's the same concept we're saying with when we talk about torque and work, or taking a vector and multiplying it by something else. Now, we could also take a vector multiplied by another vector, and we're going to see that in this chapter as well. Okay, so a vector can be amplified by multiplying it by a constant. Or what's the other word for a constant now that's not a vector? What was that other term I used a minute ago? Scalar. So let's get into scalars. A scalar only represents a quantity or a magnitude. It doesn't represent what? Direction. Okay? A scalar is simply a magnitude, not direction. Some examples? Speed is the one that right away everybody thinks of, because we always say, oh, well, what is speed? This is the absolute value of your velocity. Absolute value means the answer is always positive, thus not indicating direction. Because if my velocity were negative, well, my speed is sure still positive. Speed is the magnitude of the velocity itself. More? Yeah. Distance. Another good one. So instead of displacement, which is a vector quantity, distance is a scalar quantity. If I walk across the room and I come back to where I started, my displacement is a whopping 0. But my distance is the sum of those lengths traveled. It's the direction along the curved path taken, or the length along the path taken. Whereas displacement is your change in position. Yeah? Yeah, mass is another one. Good. Mass would be another. Chip?
I was going to say weight.
Technically, weight is a force which acts downward. So, yeah, it's still a vector. But some books will say, determine the magnitude of the weight, which means just find the number of newtons. Don't give a direction. Weight would be a vector, though, for that case. There are others. I think temperature would be another good example we've used in the past. Time. Okay? We could probably think of others. But anyway, the idea of direction doesn't matter.
How is temperature scalar one? It's like negative. Or is that?
Because the negative is, first of all, temperature should be measured on an absolute scale, which doesn't have it. So you go from 0 to 100. The temperature scale itself, it's a good question. It's always considered a scale. Why? If it goes up or down in the direction of negative.
Isn't it based on doesn't have a direction?
Yeah, I mean, if it's based off of 0, it's always going to be only upward, but we're only going to be positive numbers, not negative. Your temperature change would be a vector quantity. The temperature change, but a temperature reading itself is a scalar. Is that clear?
Even when it's like a data sign?
Think about it. If I give you a value and say, like, okay, the temperature of this fluid is 20 degrees Celsius, that's a quantity. I'm not giving any directional. Sure, it's not negative, but I'm not giving a direction. But if I said the temperature change is negative 20 Celsius or positive 20 Celsius, it means it physically increased or decreased in that direction by that much. But if I'm giving it an exact value of temperature, it would be a scale. Let me think about it more to give you a better answer then. Because if that's not clear, you're giving that look, which is good. You should think about stuff. Keep asking stuff like this, guys. If it was something I say is not clear, please challenge me. And sometimes I might have a direct answer, but that one's kind of an indirect answer, I guess. Yeah. Let me think about it, Chip, and give you an answer, or a better answer. All right, so those two things are the types of quantities or the types of values we're going to deal with, vectors and scalars. Something that's really important to recognize, a vector can never be equal to a scalar. And I know that sounds stupid, but it's like equating apples and oranges. Okay, a vector quantity on one side of an equation equals a vector quantity on the other side of the equation. What is that similar to from last year's physics course? What do you always have to have at the end of an equation on both sides of the equation? You have to have the same what?
Unit.
There it is, nice. Units. Meters cannot be equal to degrees Celsius, right? We know that? Okay, you cannot equate those two values. So again, vectors must be equal to vectors. They cannot be equal to scalars. Okay, let's go to the next slide. Let's take a look at summing and subtracting and multiplying vectors. So let's start with vector addition. For vector addition, you want to think about the fact that we are adding two vectors together. Adding two vectors together. So let's think of a physics application of this. We've got an object. Let's draw a dot, please. We'll draw a free body diagram on this object. We'll say that there's an applied force here. And this force is 20 newtons at an angle of 15 degrees. And then there's a second applied force. And that applied force is 15 newtons. I'm going to give you the angle between the forces. The angle between the forces, 12 degrees. Not the angle with respect to the horizontal, the angle between the forces. 12 degrees. So we've got these two forces acting on an object. And for the most part, with free body diagrams, what do we traditionally do? What do we do with a force that's at an angle on a free body diagram? Sorry, think back. We usually break it into its components. Very good, Chip. We break it into its x component using the cosine and the y component using the sine. Now, for the sake of vector addition, we're going to first do this with what's called a graphical method of sign. And then we'll take a look at the vector quantities. So, if I had two forces applied in generally the same direction, are they helping each other or hurting each other? They're helping each other. It's like me pushing on a couch, and I can't move it, and somebody else comes over to help me push on that object, right? Versus them being on the other side of the couch pushing against it. Our forces would be combating each other in that second circumstance. In this circumstance, they're clearly helping each other. This is an example of vector addition. Now, if I were to just simply try to add these vectors together, I can do what Chip said and break this one into its component, break this one into a component, and then I can take the second vector, break into its component, and break that into its component. And I can add together the two horizontal vectors and the two vertical vectors and get the overall answer. And that's what we did a lot of last year. Now, if I wanted to show this graphically, though, without components used, I use what's called the tip-to-tail method. Okay, and this is for graphical representations. We're not using our components using our sine and cosine functions. So what we do for tip-to-tail is as follows. We literally take one of those vectors. For addition, it doesn't matter, either vector. We take one of them and start by drawing it. So I'm going to draw the 20 Newton vector at 15 degrees. Based on the name of this method, I'm probably going to take the tip of one of them and match it up with the tail of the other. That's why it's called tip-to-tail. Again, I'll take the tip of one of them, meaning the first one. I'll point so you can see what I'm referring to. I'll take this spot right here, this tip, and I will start the tail, which is right here, of the second vector, the tail, right at the tip. So I'm going to take literally this vector and begin drawing it from where I left off right here. I'll use a different color for that so you can see. So here's my second vector. What would that angle be of the second vector? 27 degrees. Okay, Max recognized right away that I clearly drew these angles with respect to each other, not with respect to the horizontal. I said it a minute ago, but it's also clear. Look at the problem. There's no way this 12-degree angle is the whole thing if this is 15 already. So it must be an additional 12 on top of the 15, thus this angle must be 27. Even if I didn't state it, it's not logical, right? There's no way this could physically be 12 degrees if this is already 15 right here. Now, the final result of these two vectors summed together, what do you think we're going to do? Think about displacement. Imagine this is the path you traveled. I want the final displacement. How would I figure it out? How would I figure it out? But graphically, I mean, Chris, graphically, what would I do?
Draw a line between that and sorry.
Exactly. Go from the starting point to the end point. And this would be your resultant vector. This would be your resultant vector. So this method, tip to tail, is nice and it's useful when you're just like kind of sketching, right? But realistically, unless I want to start using the law of cosines, right? Law of cosines allows me to find any angle or any side in a triangle given enough information, not a right triangle. So if I look at this, it's clearly what shape? A triangle, if I look at my three vectors. So I can figure out, okay, what is the magnitude of r? And the way I could figure that out is if I knew the other two magnitudes and if I knew something about angles. Remember, to find an unknown using the law of cosines, I need to know this length, which is 20, this length, which is 15, and I need to know one of these angles at least for it to work. I can deduce and figure out one of these angles if I needed to. Could I actually look this up? Could I figure out one of these angles?
You do 27 and then, oh wait.
It's not, yeah, I was thinking the same thing at first. I think I would need one more angle to actually, oh no, I can use the law, can I use the law of sines? No, law of sines you need at least one angle to start it. Yeah, so we'd have to have one more piece of information here. I think there's got to be something more.
Could you assume that one of the 15-degree angles, the red line is going to be between where the 12-degree angle and 15-degree angle is, like, or is it not?
You mean this angle here?
Yeah, the red would be 6. Like that angle would be 6.
No, I like what you're saying though. Yeah, no, it doesn't work that way.
Question. So, right in the 27 angle, if you draw a straight line across, theoretically, don't you have to add up to 180?
Yeah, but this straight line doesn't give us this full angle.
Oh, okay.
I like your thought. That's what I think somebody was saying about, oh, if we put a line here, we get the result or what's left over from 90. But if I do that, then I'm missing part of the angle right here. Anyhow, the point being, you would not take this method if you were trying to actually figure out the sum of the x components and the y components. You would use the component method. This is to see a graphical approximation of where the resultant vector would be or what it would look like. Okay? Yeah?
I have another here. What if you did like, you continue the blue line down and then continue the blue line, the dotted line left, so then it'd be across, and then you know you could find with the 27 and then add that to 27.
So, let's see if that would work. I see what you're saying, but I think we're still going to run into an issue.
Oh, no, I'm not going to go along that blue line.
You're saying continue this
Yeah.
and continue this, makes that 27, which gives us this angle from 180. But we still don't have this angle right here, Matt.
Oh, yeah.
You see that little piece that's missing from the angle? So we have this, and that's what Karen kind of gave us with the 180, but we'd still be missing this angle here, and we don't know what this full angle is right here to get that other piece. See what I'm saying there?
Yeah.
Yeah? So I don't think I would use the tip-to-tail method to actually get a resultant. Okay, with that said, though, I want to look at subtraction. Subtraction is defined as what in math? Subtraction is defined as what in math? Finding the difference. I like it. What else? Freshman year. Oh, I didn't teach you all freshman year, but those I did teach. I use this one definition every year with every freshman math class. Subtraction is defined as what? Think about it.
It's like the difference on the number.
Okay, that works. The distance between 0 or the two numbers on the number line, that works. What else? What is it related to that we're doing a minute ago? We didn't do subtraction here, we did.
Addition.
So what is subtraction defined as in terms of addition? What is it? Okay, reverse of addition. Thank you. Adding the opposite. And I know that sounds trivial right now, but it is important for this. Just like what is division defined as? Yeah, good to know. Keep that in mind. Multiplication and division are related as well, right? So subtraction, we think of adding the opposite. So if I had vector number 1, and I'll use the same quantities, and I want to subtract the second vector, instead. So I want to take the first vector, instead of adding them together, I want to subtract them. Well, if I think about subtraction, again, I'm adding the opposite, which is like I'm doing this. Ready? Make this a plus sign here, and think of multiplying this or putting a -1 in front of that vector. I'm using symbols here, obviously, and then diagrams. I know that sounds weird, but think of adding the opposite, like a -1 multiplied by this vector. If you multiply something by a quantity like 2, what do we say is thus to the vector if we multiply it by 2? I multiply a vector by a scalar like the number 2, what would happen to it? Yeah, it would get longer, right? It would lengthen. So if I multiply by a negative quantity, what do you think will happen? Careful, a fraction would shrink. A fraction would shrink. Good. It would revert or change its direction. So really, when we think about subtraction, what we're doing is we're taking our original vector and we're adding the opposing direction. Again, subtraction is just simply flipping the direction of the second vector, which is what negating something does. When I add -3 to something, I'm really adding 3, but I'm negating that 3, right? So I'm negating the second vector, and that's what subtraction really is. I'm going to erase this piece right here as not to confuse anybody and just show from one line to the next what I was referring to. Okay, so again, whenever you're subtracting two vectors, I want you to think of the definition of subtraction as adding the opposite. Now, can I arbitrarily choose which one to reorient? Am I allowed to arbitrarily choose that? Why not, Chris? I see you're saying no. What law of math tells you you cannot just switch or choose which one to subtract from the other? Subtraction is not commutative. Very good, Karen. Is not commutative. So I can't just say, oh, I'll do A minus B or B minus A. So I can't just arbitrarily switch to this one. If I'm subtracting the second vector, I must invert the second vector, not the first. Okay? So again, if this were vector A minus vector B, whereas earlier this was vector A plus vector B. Okay, a vector symbol has an arrow over the top, or a ray. A ray on the top. Chris?
You do tip to tail of that.
And yes, right. And you would continue with tip to tail from there. So let's continue with that last piece. So we've got the first vector, doesn't look any different from the first time we did it. Oh, there we go. It's still the same thing. This is just the same thing as tip to tail a moment ago. But now with the second vector, I started where the first one ended off, but I draw it downward now. The angle is 27 still. I'm going to kind of have troubles fitting it in there, so I'm not worried too much about writing that angle. And now look at my resultant. There's my resultant R. Yes?
As it stands, these aren't solved.
So we're not trying to find the angles in the problem. We're not trying to, per se, find values like R in the problem. But over time, we should recognize that using this method, Tristan, we can find the overall force if we break things into components instead of using the graphical approach. But the graphical approach is something that can show up in a multiple choice type question, where they give you two vectors and ask, what would the resultant vector be of A minus 2B? You've got to realize you're taking the first vector, you're inverting the second vector because it's minus, you're doubling the length of the second vector because it says 2B. You follow what I'm saying? So that's where it could play a role in this kind of exam or test. So let me give you an example of that. So let's say we've got the following. Let's say we've got vector A is represented by 14 meters at 15 degrees northwest. Vector B is represented by 12 meters at 7, no, that's too small, at 32 degrees southeast. Okay, let's take a look. Can I scroll up? I'll leave a little bit if we need that other stuff still. There's an example here. So let's say we've got these two vectors, okay? And we're given, or we're asked to determine the quantity. Let's say the quantity A plus 2B. A plus 2B. The number 2, what kind of value is that again? The number 2 by itself. Scalar quantity. B is clearly a vector, A is clearly a vector. So we're taking A and we're adding twice the value of B to that quantity. So we start with this one. We need to know our directionals in this course. We're all familiar with north, south, east, west? Can I assume? Okay, I gotta ask that one always. So northwest would be north of west. Always put the word of there. Always put the word of. It makes life so much easier. Because if I had west north, it would be west of north. This is north, right? So if the directional said west north, which I can write that way, this is north, and 15 degrees west of north would look like that. But 15 degrees north of west, you start west, and you go north of west. So put the word of between your directionals in your mind always. North of west, south of east. And it allows you to draw that angle in the correct direction. So the first one is north of west. So I know that normally west is left or right. In this case, west is left. We use a general assumption here. I know in the city that's west and that's east. But when we say west on a paper, we're saying left for west, east for right. So normally this is west. But the first vector is north of west at an angle of 15 degrees. And I'm going to try to draw things to scale whenever I do so, just so that when I see it, I recognize its significance. So I have my 15-degree angle north of west, and the magnitude, or the scalar component of that vector, is 14 meters. Now, to that, I need to add twice the quantity of vector B. So what changes in vector B if I'm doubling it? Specifically, what changes in vector B? The distance, or the magnitude only. Very good. So instead of it being 12 that we're adding 24. The angle is still the same angle. The scalar component of 2 does not affect the angle. It affects the magnitude only. So really, what we're doing again is 24 meters at 32 degrees, because we're doubling this quantity in B. We're doubling B, so this becomes 24, but this remains 32. Southeast, from here, I want to go south of east. Well, this is east, and this is south of that. So I'm going to be going back in the direction that I just came from at a bigger angle. Remember, this is 15. So from geometry, you should recognize that this angle is also 15, right? Take a look where I'm pointing. This angle here is 15. They're alternate interior angles for parallel lines cut by a transversal. So really, I know that this angle is 15. So if I want to come back at an angle 32 southeast, it's got to be more than that. So I'm going to clearly draw my angle a little bit more. And this vector length should be 24 meters. And again, that's my angle, 32 degrees. So my starting point was here. I went along this vector for 14 meters at an angle of 15 degrees. We then went south of east, which comes back in this direction, at an angle of 32 degrees. And my distance traveled is now 24 meters, not 12 meters, because I've doubled it. So my final resultant, again, is from the beginning to the end. Now, what's interesting about this method is if not drawn to scale, it can be very misleading. Example, here. It looks like the resultant is almost vertical, right? Look at the resultant just in your mind. This is almost vertical. Is that like maybe a 2-degree angle east of south? See how this is slightly to the right of what you consider the vertical? It's very possible that when you sum these vectors together with components, it's not going to be an actual vertical vector resultant. Because I'm doing all of this by just freehand, right? If I were using what, would it be actually more appropriate? What could I be using? Protractor. Ruler.
Program on the computer.
Program on a computer. One more thing. If I don't have a protractor or a ruler, protractor pieces can be hard to get around because the angles are hard. But what else could I really use if I wanted to think about length and such? I guess a compass would give you some sort of degrees anyway. If you want like a central arc in there, it would work. I was thinking graph paper. You can use graph paper to estimate these values as well. Anyway, with that said though, I want to quickly, just want to stop and then start to laugh. I want to quickly just find the resulting using components. Just to practice, okay? Using components. So let's go ahead and do that. Let's break vector A into its x and y components. So vector A's x component is going to be 14 meters times the cosine of 15 degrees. But since I'm going to the left, what do I tack on to this value? Since I'm going to the left in my x direction. Yeah. The y component of vector A. So again, follow me on the diagram if it's not clear. The x component was this. I'm going to draw it. Or I'm going to highlight it, I guess I could say, right here. That's the x component of the first vector. And then here's the y component of the first vector. So, thank you. So I'm not looking at the red vector right now. I'm looking at the black vector. So I go left in the x, which is negative, and I go up in the y direction, which will make this positive. And that'll be a positive 14 times the sine of the angle. So those are my vector components of A. Somebody else tell me about B. Tell me about B's vector components. And don't double it yet. We'll double it in a moment when we sum them together. But give me simply the vector components of B. Chip.
Well, the x component would be positive because it's going so it would be 24 meters times cosine.
And I'm going to, good. For B, I'm going to just leave it as 12 for now because we're going to double B in a minute. Yeah. And then good. So we have cosine of 32 degrees. Why again? I know Chip knows, but why is Bx positive? Why is Bx positive in this circumstance? What are we thinking? Is the rationale there? Huh? Yeah, we're going to the right. So if I look at the red vector, again, whenever you're given a vector, think of making a right triangle. Follow my finger here, please. Starting at the starting point of the red vector, I go right, and then I go down. To the right is positive for x. Down, though, is... So the by value is going to definitely have a negative quantity in front of it. And we're using the sine of 32 degrees. Very good. So these are the vector components of A and B. And if we want to find the overall resulting in blue, R, we can sum together the individual components along the corresponding directions. So x's sum together with x's, y's sum together with y's. And then we can put the triangle back together using Pythagorean theorem. So let's go ahead and show that mathematically below. So my goal again is to figure out this quantity right here, right? A plus 2b. So really, for the x component of the resultant, I'm going to have negative 14 times, and I'm just going to use numbers for now, cos 15, plus 2 times the x component of the second vector. And again, why am I putting a 2 here? Because the 2 comes about from here right here. All right, we're doing a plus double the second vector. This was the second vector. These are the x and y components. I need to double them when I'm adding.
So how does adding get Rx?
It's going to give us Rx, and then we're going to get Ry. And let me show you on the diagram. This starting value right here, and this is hard to draw, Tristan, hold on. See this right here, the resultant? This is Rx. This is Ry. So it's really tough to see because of the triangle being so small. But Rx is going to be, thinking about this went all the way back, this red vector border all the way back over here, and maybe we ended up just to the right where we started. So Rx is going to be that little leg, Ry is going to be that leg, and then using Pythagorean theorem, we could find the hypotenuse by adding the squares and the square root Pythagorean theorem. So we're going to sum together this quantity plus this quantity. Notice the first was negative. We went left. The second one was positive. We went right. We doubled the 12, which is where the 24 comes from. And then we're going to do the same thing for the y component. Oops. We're going to say here, we've got 14 times the sine of 15 plus 2 times negative 12 times the sine of 32. Again, these quantities right here are coming from AY and BY summed together, but doubling BY because we were doubling the vector B. Can somebody help me out real quick if you don't mind? You got numbers? You got it already, Bridge?
Yeah,
Thanks.
for Rx I got 6.83, and for RY I got negative 9.09.
Okay. So clearly, thank you. Clearly, our diagram is not drawing the scale. Does everybody agree with that based on these numbers? I mean, this little Rx that I barely drew in that Tristan asked about looks like a tiny, tiny length relative to the Ry, right? But yet, look at the numbers, the magnitude. Rx is about 2/3 of Ry. So this triangle is not perfectly done, and that's what I was getting at earlier. Clearly, our resultant vector is really about 6 meters to the right and then 9 meters down. That's our x, that's our y. We want to find the overall resultant r, and we want to find the angle theta that it's at. Okay, so again, it's clearly not drawn to scale when we sketch using tip-to-tail method. We sketch using tip-to-tail method. Okay, so let's get the final resultant. That's going to be the resultant. Actually, I'll just leave without the vector line because I don't have an angle yet. And then the angle theta will be the tangent inverse of, I want y over x, so it's going to be and really what we'd have is this. So it'd really be absolute value. Okay, those would be the two values we're looking for. Where did the r come from? Pythagorean theorem. A squared plus b squared equals c squared. But how do I get c by itself? I take the square root of both sides. God bless you. I'm going to, at times, just make assumptions that you see what I'm doing if I jump a step. If that's not clear, just simply ask. I'm happy to revisit stuff, but at the same time, I'm going to going forward, not show every single step. If it's simple math, and what I would consider simple, but what I consider simple math is not always the same as what you consider simple math. So if it's an issue of understanding, I'd rather pass and sit there and be like, I feel dumb, I shouldn't ask this question, I'm not really sure we did. Ask the question if you're not sure. Okay? So again, Pythagorean theorem is what gives us this, and this is from trig. It's a right triangle at the top. Okay? If I look at a right triangle, this is the opposite, this is the adjacent. If I recall, SOHCAHTOA tells me that I'll be using the tangent function if I've got opposite and I've got adjacent. And there's my right angle in the triangle. Okay, so I'd say the tangent of theta equals Ry over Rx. So that theta equals the tangent inverse of Ry over Rx. Okay, these are theories that you've probably seen already last year in physics, but I don't want to assume that it's, easy to see. What do we get for number? Yeah, Karen, ask.
So it's plus or minus, so it's always plus when you're doing radicals?
Here?
Yeah.
Yeah, because the original formula was a squared plus b squared equals c squared, and then I got rid of the squared here by taking the square root.
But the square root is always positive, right? Because
Yeah, because you're always going to be squaring this quantity, so you can kind of drop negative if you want. That works too. Yeah, and even here, Kara, the angle from the diagram will tell us whether it's southeast, northeast. So the negative for 9.09 doesn't really matter. We're getting the magnitude of theta. But we know, based on our diagram, that the answer is going to be southeast. Right? Because we're going literally east according to x, and then we're going south according to y. So this angle, whatever it is, will be at an angle southeast. Numbers? Numbers? We have them, Spence? Go ahead.
11.37 for
And theta you got?
53.079.
Now, in this course, we will use degrees. If a time comes where radians are there, I will tell you and we'll talk about that. But for now, assume everything is in degrees. When we plot sine and cosine waves later with oscillations and vibrations, we'll get into a little bit with radians there with plotting. But for the sake of vector quantities, you're never going to express angles in radians because they're not intuitive. For example, you probably all know, what is pi over 3 in degrees? Pi over 3, what would that be in degrees? 60, because pi is 180. That's kind of how you do it, right? You always think pi is 180. But in life, you're never going to give an answer and say, oh, it's at, pi over 11 radians. Like, it's not logical. Everybody knows what 90 degrees is. So if I said 10 degrees, you know that's only a small angle. If I said 40 degrees, it's about halfway there, it's vertical. But you wouldn't give values in radians in real life. Now, that's not to say, though, that radians don't have their importance, and they do. So I want to make that point clear. But you'll see that everything's going to be in degrees for vector quantities and diagrams. Okay, so our final answer, let's write it one step, is vector r equals 11.37 meters at 53.1 degrees southeast. Now, a lot of work to get one answer for a vector that we could approximate using the tip-to-tail method. But as we noticed, the tip-to-tail method is not always a good thing to use. Thank you. Does that make sense? Okay? All right. So that is literally, by the way, the first 2 pages of the book. Okay? Background math is like 7 pages in the first chapter. This is the first 2 pages of the Barron's book. So what's in that book is very, very simple. But I'm going through examples to take you through this. So obviously the book will help you when it comes to like refreshing your memory, or if you like to read ahead of class, that might be a good thing also sometimes. But when it comes to going through a lot more examples, I'm going to do way more in class than what you're going to see in the actual book. All right, so here's what I want to do. What I'd like you to do is the following. I'd like to design an experiment that allows you to calculate average velocity and estimate instantaneous velocity using a motion detector. That's your premise for the first lab of the year. It's not a tough one, it really isn't, but it's something that you haven't done probably in the past, because I think you said you had to use motion detectors last year. I know we used them briefly in our class, so I know you're familiar, but I'll go through a run through how they work. But this is your general goal for this first lab of the year. Now, there are going to be times in the year where a topic may present itself. If some of you are ahead in your math course, and I'm going to call you out, Max. I know Max did you calc last year. So there might come a time where, like for you, Max, this is probably going to be very easy because I know you do this in calc already. The concept of instantaneous versus average is covered in your calculus class. You guys are all going to do it in calc, probably in like a week or two, is my guess? You are?
Yeah.
Nice. Awesome. So you have an idea of what you need to be doing. So that's a good starting point. But you're, I'm guessing, only using like data, right? You're not actually doing stuff in lab in calc right now?
We found the derivatives using the
Doing derivatives already?
limit process.
Using the limit process?
Yeah.
Okay, awesome. And the way we're going to get to derivatives, I can take you to the limit process, but I'm going to start using derivatives and go through the rules of derivatives. So you might get a little bit ahead of that at some point. But for this sake, this is like the limit process, very much like it. So with the limit process, you talk about the secant line and the tangent line. Has Mr. Lyons drawn that and showed how the secant line, the 2 points get closer and closer, becoming a tangent? That's very similar to what we're going to do tonight. But we need to have data. We need to actually perform the experiment. Okay, so here's what I want to do. Not going to give you the setup, like I said. I want you guys to think about how you would set this up. I'm going to give you the tools to do it. So what I'd like to do for now, let's go Bridge and Pat together. Spence and Chris, this works. Max and Tristan. Matt and Emily. Kara and Chip. Okay, and I'm going to change your parameters of every lab, but I want you to work with different people. I don't want you to work with the same person every time. I want to start thinking about, like, as we go throughout the course, who works well with others, and maybe a stronger student in one area with a weaker student in other areas. So I might back and forth change your partners as we go from lab to lab, as they get to know you better as a calculus physics student. Okay? So what we're going to have for this is vernier probes. We have, in this category over here, motion detectors. Now, the motion detectors connect directly to the probe. You can either connect to these probes on the side, which is called an analog port, or the top, which are the digital ports. It says dig 1 and dig 2. You have to kind of pop this open to get in here. My hands are weird, so I'm going to take. There's a pen in here. This pen slides out. Stylus. It's easy to properly sort of fit. So, either the digital port or the analog ports receive the sensor. I don't remember, I think this is digital. So if it doesn't show up, you connect it together. So as soon as you plug into a port, the device will recognize motion detector attached. So it will start to show a distance. If it's not showing a distance and you're trying to get the analog port, it doesn't fit, it goes to the digital port. It's one of them. And that's to do with older sensors versus the newer sensors that they're going to use. You're not going to really be using a microphone or this stuff over here, so don't worry about it as much. The power button is on the top. Press the power button once. It'll give us a second, it'll start to turn on. Some of these have not been touched all summer, most of them I would say. So there's a chance it might come up and say, like, would you like to calibrate the screen? You can hit yes. Remember having you touch 5 different hash marks to calibrate the sensor on the screen. But if you look at this right now, you'll notice there's nothing happening. All it says is mode, rate, and duration. Along the top here, I'll see that I have a graph option. Can everybody see this? Is the angle good? Can you see this angle? Yeah? Because I can mirror this in the screen also. Okay. You can then see a table. After that, you can see what's called a notebook, which gives you instructions to use this, or like a lab viewer book. And then at the very end, it looks like they have like a note you can write yourself. So if you wanted to write like a note down. We're going to use these a lot, but they're not very, what's not user-friendly, but they're not very smooth when it comes to exporting from here to something else. So when we get values from here at times, it might be worthwhile to either try to save the information on like a flash drive over here, or if you get data, to at least write down your data in your logbook. So you may not have a 1/2 inch binder yet, and I mentioned that for your lab book to have. So if you don't have that, don't worry. You can just use any paper and punch holes in it and put it in your lab binder afterward. So any paper is okay today. But I'd like you, for the sake of labs, to be taking down data on actual paper. You can use your iPad for other things as well. So if there's an image that you want to get, like a graph, and you're having trouble exporting it, sending it to your email because maybe the Wi-Fi, like this one, the Wi-Fi is working, so it's fine. You can probably send a graph elsewise. But you could also just honestly get really close to a graph, so I take a picture, and then just crop the picture so it looks nice afterward. Okay? But you might want to use graphs to reference. So in your lab notebook, although you might rip a sheet out today and put it in your binder, tomorrow you can maybe take the graph you have, print it, or put it in like a notability file, print that, and add it to your lab book. So your raw data and the stuff that you're collecting should really be on paper. But your lab report could all be done in Notability. Is that clear what I'm saying? So you can absolutely use Notability and use a computer to write your lab. And I would actually recommend that personally. But your data and the work you do during the lab should really be recorded on paper itself. Okay? In addition to that, when you're recording data, this is the one time that I do recommend that you use pen. Okay? Because you really should not make the lab work for you. Does that make sense what I'm saying? If your data, for some reason, isn't working, you shouldn't just erase it all with a pencil or in Notability, erase it and it never appeared. There should be a record of the fact that the data didn't work for you the first time. And then what did you have to do? You had to adjust and adapt to make the experiment work the right way. Maybe, for example, when you're using the motion detector, you never calibrated it. So, although the person was walking like this, the machine maybe thought that this distance was a meter to start. So all of your values are off by a meter. And you realize that after you take all your data, I don't want you to cross off that data. I want you to write yourself something that says, Unfortunately, this data was done where the machine wasn't calibrated, so we're going to remeasure our data. Is that clear? As scientists, you should have a track and a record of all the work you do, whether it's right, whether it's wrong, whether it's acceptable, whether it's incorrect procedure or not. You should still keep records of this stuff, and then you adjust as you go through the lab, and when you write your lab report, you reflect on this idea. Part of your conclusion is reflecting on the procedure you took, because these are inquiry-based labs. Okay, so part of the conclusion is not just answering questions for me, but analyzing the procedure you took. Maybe the first day the procedure you guys take wasn't the ideal route. You write about that at the end. Okay, is that clear? You have to understand when you're doing things right or wrong, but at the same time, not just throwing it out the window because it was wrong. All right. So again, I'm going to give every group a probe. Probably not going to have time to start this today because we don't have as much time left, but maybe start with writing out a procedure. Talking about what you're going to do. Once you collect your data, because now that you've done the secant and tangent line and calc, this shouldn't be too hard actually to have at all. So once you collect your data, what are you going to do to get the average velocity? How many times are you going to do it? You're going to get the average velocity from here to here, maybe here to here, here to here, here to here, and then estimate the instantaneous here? Or are you going to start and move your coordinate this way? It's up to you to decide. I'm not going to tell you, I need to see 5 average value or average velocity calculations and only 1 instantaneous approximation. It's up to you to decide with your partner what is necessary to get your point across. If only 2 average velocities are needed, and then you estimate 1 instantaneous, and it really gets the point across, then that's fine. But it has to make sure that it's clear in your write-up that that was all you needed for it. So it's up to you to decide how you're going to approach your procedure, your data collection, etc. Okay? So here's what I'm going to do. Instead of taking all these out right now, I'm going to take one out and come by group to group to show you how it works. But while I'm doing that, I want you to start with your partner, just designing the lab. So what I want you to do is write out a procedure. Procedure can simply be numbered. 1, 2, 3. Maybe before the procedure, list the items that we need for this. Motion detector, vernier probe, a vernier lab quest, and a motion detector device. And you want to actually call it that. Motion detector device, vernier lab quest 2. Because these are the lab items that all AP class is using across the rest of the country. So you should be familiar with these things because they're so general.
So should we be writing that stuff down on paper or?
So for the beginning part, everything should really be on paper that you're doing in the class. It's annoying because then you're going to transcribe it onto like an electronic version when you submit it at the end of your report. So for this, you really do want to be using paper. Like, could you take a picture of it, maybe PDF later on in there, you said? You could, but it's going to be very sloppy. You should get used to making your lab reports professional in nature. So they really shouldn't be like, I guess they could be raw images though. You could have raw images as figures, that works, but for your procedure later on, it really should be typed up at the end. But like your raw data you collect, if you don't want to make a new table in Notability, the raw data, that could be an image, or a figure of a graph from the LabQuest device. That could be an image that's inserted. But any text, anything that you write, any prose, should really be typed in the end for your report. So if you want to like write a very, very shorthand version of your procedure right now, and then when you write the lab at the end, be a little bit more explanatory or explain a little bit more of it, that's fine also. Okay? But again, the idea of the lab book is so that you shouldn't be making your data work for your lab. You should do the lab and understand your data and recognize whether you need to change it. Let me get one of these probes out so you guys can see. I'm very good at picking locks. I know that's random, sorry.
Yeah, if you have a pumpkin carver, it's easy.
A what card?
A pumpkin carver. Stick a lock,
A pumpkin carver works.
yeah, you put a pumpkin carver and then a detention wrench in there, and the pumpkin carver, when you use it, just hits all the.
Why do you know this? I
I
asked.
saw it on Snapchat.
Nice. Well, I need your help. So this lock always gets jammed. That's why I got it. So we've got enough motion detectors for every group. So each group will have their own. But for today, I'm just going to come around and show you it from group to group. If you had me last year, you probably know how to use it, but I'll remind you just in case. this is digital, by the way. The digital port. Come you guys first. So, the motion detector with flowers. You can use a card on a track or an object. Since we are objects, we're going to use objects, but you can set up a track and use a little card going back and forth, and that's completely fine. And we have little cars up in the cabinet there, and the track's here. So if you're an experiment, you want to use a car, a track, you put it right in the track, and that could work. Or you could use an object in a person. Now, the motion detector itself is here. It sends out a sonic pulse every time. The time it takes to get back is measured based on the speed of sound, and the time it takes to get back, it calculates the distance the object is away. The idea is that the speed of sound is a constant, 130 meters per second. Now, in the actual lab device itself, the distance increases. About, the distance should increase. When I'm here, it should say 0, it's pretty close, it's not exact. When you're here, what you can do is you can put your hand here, you can do this, put your hand right in front. And when you're, and put it like almost up against it. Keep going, yeah. So this should be 0, right? So what I can do is at this point I can put a sensor here, and I can 0 it out. So calibrate is the normal command we used last year, but some of these have 0 not calibrate. So 0 the motion detector, so it gives a basic. Now move away, and you'll see it start to increase from there. It's a little bit thick, so do your best with the numbers you're going to get. Now, to use the device, you're going to press play. This will only record zone for 5 seconds. So when I click on 5 seconds duration, I can change it to more than 5 seconds. I can make it 30 seconds. And this is rated, it's taking 20 samples every second. So the frequency F is 20 pulses per second. That's a very, very high frequency. You can leave it the way it is, you can make it lower, it doesn't really matter. But I'll change the time duration for sure. Okay? Once you play, it'll start taking data. If you get enough data, you can press stop or let it run for the whole 20 seconds. After that, now the graph of the motion itself. We are really focused on the position graph, not the velocity. So I'll go to graph. Sorry, show graph. Then we're only going to show graph because we only care about position. The velocity graph of the detector comes out like crap, so don't even use the velocity. Remember last year how poor it was? Yeah, it was like shooting up and down. So only use the position graph. And what you'll see is if your cart or object moves away, the position would increase versus decrease. And you have to talk about this concept. Okay? Does that make sense? All right, we're going to move to the next group. Continue writing the procedure. We're going to talk about what you're going to do after you collected your data. Anybody have the bell for this class? Anyone know? 43? 2 minutes. Okay. You know how to use this right now. I'm going to jump. You remember these? Okay. I'm going to jump through the groups and start explaining and I'll come back. I'll start next class. I'll explain it to you guys. Okay? Yeah, is that cool? Actually, you want to sit in and look at this. If you're just waiting to hang out.
Kind of remember.
So, the motion detector itself is a sensor. This is the sensor. Command ratio looks like a speedometer. And it senses the distance away from the actual device. It sends a pulse out using sound waves. The speed of sound is 330 meters per second. It can take the time it takes the sound wave to return, and it can know the speed of the sound, it can measure the distance away using V equals X over T. Assuming it's a constant speed, which the speed of sound we assume is constant. So as you move further away, because it takes longer for the pulse to return, the distance measured increases or decreases. Now, depending upon the setting, if you guys want to use your object, you as a person, or if you want to use those tracks and some parts up there, you change the setting. So if it's a track on a cart, you're going to put it on this. If it's a person walking back and forth, like we did last year in the gymnasium, you change the setting to this. If it's going to be a person, the recommendation, if I remember from last year, is to hold this cardboard first. Because the pole sending back, then there's legs, different colors, different materials don't work well. So holding a flat piece of cardboard as you walk allows the sensor to use a consistent barrier to bounce the sound wave off.
Is there a free fall option on there?
There is. There's a whole free fall thing here. We'll do free fall as an experiment. We'll do 1D
Or
motion.
should I like read it for this?
Could you do this procedure as a free fall right now? Sure, you could do this as a free fall. It doesn't have to be horizontal motion. If you want to. Obviously, the thing would be you have to put the device like this, put an object, and then just drop it below. I don't know if they look out. Well, you can do that. So the motion can be vertical or horizontal. It's up to you to decide. So you pick this one. I'll see you guys on Friday. There's no homework right now, by the way. If I want to change that, I'll put it on Google and let you know. I'll send you an email if I add homework to Google in the next day or two. Okay, I might add a small assignment And if I do, I'll tell you. Already accelerating around that 181. So you guys get this points in here. You're gonna have to tie the car to the weight and run the pulling around drop. So next play, we'll get some forward. That's considered what if the car, if the device is measuring the car, it's actually a lot of motion. If the device is measuring the dropping weight, it's a vertical. But it doesn't matter. They're the same position time graph, really. Because the motion would be this. Because it's accelerated motion. If we're moving away at a constant rate, it would look like that. And part of this is approximating velocity, so you want to have accelerated motion this way. You do not want this to be a constant velocity example at all. Exactly, or else the slope, the approximate secant line and tangent line would be identical. Right? And you can say that.
And it's also, if it's a curve, then you can actually have like a tangent line with the x-axis.
Yeah, at several locations also you could approximate the instantaneous velocity whenever it's something curved, because that tangent line changes slope. All right, guys, have a good day.
Thank you.
You're welcome, guys. Have a good day. I'll send you an email. All right.